and then we'll get started. All right, state time. Confession time. I went a little overboard and packed way too much into this chapter. It's ostensibly about the state Gang of Four design pattern, but I can't talk about that and games without going into the more fundamental concept of finite state machines, or FSMs. But then once I went there, I figured I might as well introduce hierarchical state machines and pushdown automata. That's a lot to cover. So to keep things as short as possible, the code samples here leave out a few details that you'll have to fill in on your own. I hope they're still clear enough for you to get the big picture. Don't feel sad if you've never heard of a state machine. While well known to AI and compiler hackers, they aren't that familiar to other programming circles. I think they should be more widely known, so I'm going to throw them at a different kind of problem here. This pairing echoes the early days of artificial intelligence in the 50s and 60s. Much of AI research was focused on language processing. Many of the techniques compilers now use for parsing programming languages were invented for parsing human languages. We've all been there. We're working on a little side-scrolling platformer. Our job is to implement the heroine that is the player's avatar in the game world. That means making her respond to user input. Push the B button and she should jump. Simple enough. Okay, so we have a heroine that has the handle input. So we remember that from the the command pattern. Takes an input. If input is press B, y velocity equals jump velocity. Set graphics, image up. Oh, image jump, because it's the jump graphics. You're going up now. Spot the bug. Well, I guess we're not using the physics with plus. Let's see. If input is press B, well, if she holds B, if the player holds B, our heroine is going to continuously jump forever. It's going to fly now. There's nothing to prevent air jumping. Keep hammering B while she's in the air, or just holding B, I suppose, and she will float forever. The simple fix is to add an isJumping Boolean field to heroine that tracks when she's jumping, and then do, okay, so we put B, if not isJumping, I may have done exactly this myself. There should also be code that sets isJumping back to false when the heroine touches the ground. I've omitted that here for brevity's sake. So I think I have this type of logic exactly in both of the Infinite Runner games. Next, we want the heroine to duck if the player presses down while she's on the ground and stand back up when the button is released. Okay, so heroine handle input, our input, yeah, A. No. Cool, that froze. Back to me. Nothing bad yet. Still using like 0.7% of the CPU, so we're cool. All right, so yeah, we have basically a bunch of if else ifs. So like input press down and is not jumping, set graphics image job, else if, okay, release down. Okay, so that's getting fun. Spot the bug this time. Okay, so let's see what the bug is. Heroine handle input input equals press. Okay, so if we're pressing B, else if, okay, so we're not jumping. if the input is pressed down, so we can't press jump and press down at the same time, which makes sense. If we're not jumping, set the graphics to duck. Else if input is released down, image to stand. So we have to like undo the down. Does that mean we can do down twice? With this code, the player could press down to duck, press B to jump from a ducking position, release down while still in the air. Yeah, that's true. I guess I didn't think that was a bug because I've actually done that in several games. You know, oftentimes it's like actually part of the, it's like usually a smaller jump, like a lower jump. The heroine will switch to her standing graphic in the middle of the jump. Time for another flag. Right, so now we're going to have to do if is ducking. Next, it would be cool if the heroine did a dive attack if the player presses down in the middle of a jump. Okay, so now we're going to have... Okay, so is jumping... Wait a second, where is this? Input press down. Okay, so if we're not jumping, set is ducking to true, and then we're ducking. Otherwise, so we are jumping, is jumping false and dive straight to the ground. So that's, I guess, like a one frame, you're back to the ground immediately again. Bug hunting time again. Find it? Yeah, because like, yeah, unless our dive takes one frame and we're like back on the ground instantaneously, well, actually there won't be a time that we stop setting the graphics to image dive. Will there be? So we can now like dive multiple times, or we can jump while diving. That seems to be the problem. We check that you can't air jump while jumping, but not while diving. Yet another field. Something is clearly wrong with our approach. Every time we touch this handful of code, we break something. We need to add a bunch more moves. We haven't even added walking yet. But at this rate, it'll collapse into a heap of bugs before we're done with it. Those coders you idolize who always seem to create flawless code aren't simply superhuman programmers. Instead, they have an intuition about which kinds of code are error-prone, and they steer away from them. Complex branching or mutable state, fields that change over time, are two of those error-prone kinds of code, and the examples above have both. Finite state machines to the rescue. In a fit of frustration, you sweep everything off your desk except a pen and paper and start drawing a flowchart. You draw a box for each thing the heroine can be doing: standing, jumping, ducking, and diving. When she can respond to a button press in one of those states, you draw an arrow from that box, label it with that button, and connect it to the state she changes to. So, okay. This is actually interesting. I've never drawn like a curved flowchart. Usually I draw it like sort of in that top-down hierarchy method. All right, so press B, jumping. Press down, so while jumping, you can go into diving. You're starting standing, I guess, and then you can go this direction. When you're standing, you can press down to go into ducking, which you release down, you go back to standing. Congratulations, you've just created a finite state machine. These came out of a branch of computer science called Automata Theory, whose Automata Theory, whose family of data structures also includes the famous Turing machine. FSMs are the simplest member of that family. The gist is, you have a fixed set of states that the machine can be in. For our example, that's standing, jumping, ducking, and diving. The machine can only be in one state at a time. Our heroine can't be jumping and standing simultaneously. In fact, preventing that is one reason we're going to use an FSM. A sequence of inputs or events is sent to the machine. In our example, That's the raw button presses and releases. Each state has a set of transitions, each associated with an input and pointing to a state. When an input comes in, if it matches a transition for the current state, the machine changes to the state that transition points to. For example, pressing down while standing transitions to the ducking state. Pressing down while jumping transitions to diving. If no transition is defined for an input on the current state, the input is ignored. In their pure form, that's the whole banana. States, inputs, and transitions. You can draw it out like a little flowchart. Unfortunately, the compiler doesn't recognize our scribbles, so how do we go about implementing one? The Gang of Fours state pattern is one method, which we'll get to, but let's start simpler. My favorite analogy for FSMs is the old text adventure games like Zork. You have a world of rooms that are connected to each other by exits. You explore them by entering commands like go north. This maps directly to a state machine. Each room is a state. The room you are in is the current state. Each room's exits are its transitions. The navigation commands are the inputs. I was going to say, enum sounds exactly what they were talking about with the different states. Enums and switches. One problem our heroine class has is some combination of those Boolean fields aren't valid. Is jumping and is ducking should never both be true. For example, when you have a handful of flags where only one is true at a time, that's a hint that what you really want is an enum. In this case, that enum is exactly the set of states for our FSM. So let's define that. Enum state, so we have standing, jumping, ducking, and diving. There is no such enum in JavaScript, unfortunately. I was almost thinking that maybe you could create one with like a class. You can do some crazy weird stuff with that. But I don't necessarily think that we should go there. There might be libraries and NPM that you can download for that. Especially if you use TypeScript. That will give you enums. Instead of a bunch of flags, heroine will just have one state field. We also flip the order of our branching. In the previous code, we switched on input, then on state. This kept the code for handling one button pressed together, but it smeared around the code for one state. We want to keep that together, so we switch on state first. That gives us, okay, so void heroine handle input, input, switch state. So switch off of whatever the state is, and my guess is that's going to be implemented like locally to this class. So case state standing, if input is press B, off of the state, then basically set the state to state jumping. Yeah, the underscore is basically showing us that it is internal to this class. Our y velocity we're going to set to jump velocity, and our set graphics we're going to execute that and hand it image jump. Else if input is pressed down, okay, so for state standing, then if we press down, we go to state ducking and all that. And then, okay, so we set state is now we're in a ducking state, and now we're going to do the image duck, and then we break after these two, so that's the one case. Then if we're jumping, if we press down, we switch to diving, and break after that. If we are ducking and we release down, we are standing. This seems trivial, but it's a real improvement over the previous code. We still have some conditional branching, but we simplified the mutable state to a single field. All of the code for handling a single state is now nicely lumped together. This is the simplest way to implement a state machine and is fine for some use cases. In particular, the heroine can no longer be in an invalid state. With the Boolean flags, some sets of values were possible but meaningless. With the enum, each value is valid. Your problem may outgrow this solution, though. Say we want to add a move where a heroine can duck for a while to charge up and unleash a special attack. While she's ducking, we need to track the charge time. We add a charge time field to heroine to store how long the attack is charged. Assume we already have an update that gets called each frame. In there we add, okay, so if state ducking, charge time plus plus. If the charge time is max charge, then just call super bomb. Like there's no button press for that. If you guess that this is the update method pattern, you win a prize. We need to reset the timer when she starts ducking. So we modify handle input. Okay, so handle input, state standing, if input is pressed down, state ducking, charge time equals 0. Will that cause charge time to always be 0 now? Because every frame we're checking this. Oh no, if we're standing. So when we stand up, never mind. I misread that. All in all, to add this charge attack, we had to modify 2 methods and a charge time field onto heroine, even though it's only meaningful while in the ducking state. What we'd prefer to have is to have all that code and data nicely wrapped up in one place. The Gang of 4 has us covered. The state pattern. For people deeply into the object-oriented mindset, every conditional branch is an opportunity to use dynamic dispatch. In other words, a virtual method call in C++. I think you can go too far down that rabbit hole. Sometimes an if is all you need. There's a historical basis for this. Many of the original object-oriented apostles, like Design Pattern's Gang of 4 and Refactoring Martin Fowler, came from Smalltalk. There, if then is just a method you invoke on a condition, which is implemented differently by the true and false objects. But in our example, we've reached a tipping point where something object-oriented is a better fit. That gets us to the state pattern. In the words of the Gang of 4, allow an object to alter its behavior when its internal state changes. The object will appear to change its class. That doesn't tell us much. Heck, our switch does that. The concrete pattern they describe looks like this when applied to our heroine. A state interface. First, we define an interface for the state. Every bit of behavior that is state dependent, every place we had a switch before, becomes a virtual method in that interface. For us, that's handle input and update. All right, so I think this is where we get to start coding. The previous sort of code examples were just how we end up doing it, but this is the actual implementation. So this looks like we're going to have virtual. I believe virtual is essentially the interface. Yeah, that's what he said, interface. So let's go ahead in Playgrounds. I'm going to create, I think I can only need to call this, what is this, state machine? Or I guess state pattern. .js. So we're going to create our interface in here. So that's going to be our heroine state. And looks like, so we're going to have our constructor that doesn't seem to do anything. And then we have handle input that takes in the heroine. and it takes in the input. And we're also going to have an update, which takes in the heroine, and that's it. So it's interesting that we're going to have this like heroine state, completely separate object, as it were, or class. I guess it's an interface. So we're gonna have the heroine that implements heroine state. Classes for each state. For each state, we define a class that implements the interface. Its methods define the heroine's behavior when in that state. In other words, take each case from the earlier switch statements and move them into their state's class. For example, we're going to have a full class for each state that we have. That's interesting. Okay, so we're going to have a ducking state. Which extends the heroine state. Okay, and so it's going to make ducking state, charge time. I think this is the constructor here. So we have our constructor that doesn't take anything in. Good morning, Pollux. Hello. So we're going to set charge time to 0. So this dot charge time equals 0. Oh, thanks. It's getting like really, really long. And if I don't have this, it's like super over my eyes. And so like, okay, whatever I can do, it's not long enough that I can go like straight back yet. And it's too hot these days to put like on some kind of like hat. So plus also I don't want to like have a hat that has a bill that like covers my head, my face. So yeah, funky hair, COVID hair. I think a lot of us are growing our hair out, or like just shaving it off. That I guess that's the other option. But like, how long is your hair now? All right, so we created the ducking state, 10 inches. Well, we'll see how long this entire thing lasts. My wife has started talking about potentially giving me a haircut. So if suddenly I show up with a lot less hair, then you know what happened. All right, so now we implement our handle input from this interface. So we have the handle input that's going to take in our heroine, and it's going to take in our input. And we have, I mean, it is an if statement. So if our input is equal to release down, which of course would be created up here. So it would be something like const release down equals something like whatever the down arrow is. It's like down. Yours is 20 centimeters long right now. I don't have a ruler up here, so I forgot how long is it? Is that long? I don't know. I'll have to go take a look at the ruler later. Sort of like visualize what that is. Release down. Okay, so it goes down. So like, for example, it might be something like that. Or it might be like what is it, like ampersand 1 5, something like that. It might be like the ASCII code. 7.8 inches. Okay, so you're almost there. All right, so if it's released down, then here this is where we set the graphics to image stand. So heroine.set graphics image stand. And then we have the update function. So this takes our heroin. This is where we now have, okay, charge time, plus plus. Might as well do plus equals to 1 is what I usually do. Okay, so if this dot charge time is greater than max charge. Am I into web security? I haven't done too much with web security. I basically know I have like some. I don't really have a security background. It's more of I have. I've worked with security people in the past. I do not do any hacker stuff. And that's it for our ducking state. Note that we also move charge time out of heroin and into the ducking state class. This is great. That piece of data is only meaningful while in that state, and now our object model reflects that explicitly. Next, we give the heroin a pointer to her current state. Lose each big switch and delegate to the switch instead. Okay, so if I were to like copy this in, see what this is. So class heroin, bring you up here. Now heroin, do you have to extend from one of these classes? No, it does not. So we're gonna have our virtual, so handle, something like that. Okay, so we have handle input that takes in an input. And so this we're gonna say, okay, set our internal state. So we're gonna essentially do this dot state dot handle input. So like run the handle input on this dot state. So if we have ducking state stored in here, we're gonna run the ducking state. And then pass it in our input. And then we have update, which also does, okay, this dot state dot update, and we're gonna pass it this, the heroin itself. And then state is just showing that's private, so we don't really need that. So this is interesting. How do we set the state initially? I would think like maybe during a constructor, we set it like the walking state or whatever that is. Heroin is just an E away from heroin. Oh, I never thought of it that way. Words are weird. English is weird. In order to change state, we just need to assign state to point to a different heroin state object. That's the state pattern in its entirety. This looks like the strategy and type object patterns, and all three have a main object that delegates to another subordinate one. The difference is intent. With strategy, the goal is to decouple the main class from some portion of its behavior. With tiny object, the goal is to make a number of objects behave similarly by sharing a reference to the same object. With state, the goal is for the main object to change its behavior by changing the object it delegates to. Where are the state objects? I did gloss over one bit here. To change states, we need to assign state to point to the new one. But where does that object come from? With our enum implementation, that was a no-brainer. Enum values are primitives like numbers, but now our states are classes, which means we need an actual instance to point to. There are two common answers to this. Static states. If the state object doesn't have any other fields, then the only data it stores is a pointer towards the internal virtual method table so that its methods can be called. In that case, there's no reason to ever have more than one instance of it. Every instance would be identical Anyways, if your state has no fields and only one virtual method on it, you can simplify this pattern even more. Replace each state class with a state function, just a plain vanilla top-level function. Then the state field in your main class becomes a simple function pointer. In that case, you can make a single static instance. Even if you have a bunch of FSMs all going at the same time in that same state, they can all point to the same instance since it has nothing machine-specific about it. This is the flyweight pattern. And we already implemented this flyweight pattern before. So that would basically be taking like that state and shoving off somewhere else that's, handles everything, all the similar stuff. Where you put that static instance is up to you. Find a place that makes sense. For no particular reason, let's put ours inside of the base state class. Okay, so we have the heroine state. We have the various, standing state, ducking state, jumping state, and diving state. And then that is other code. Each of those static fields is the one instance of that state that the game uses. To make the heroine jump, the standing state would do something like, so input equals press B. Heroine.state is heroine state jumping. Oh, so this would essentially be like a static off of heroine state. Is there a way to do that on here? Can I do static in JavaScript like this? So static, I could do standing equals standing, something like that. Or is it going to be something like const? Nope, that's not it. I think you seem to be fine. Heroine, okay, so heroine state dot standing is now a string. Okay, so if I do that for all of these, so static, here, let's just copy you in. And basically we're going to have standing, ducking, jumping, and diving. And if I copy you equals quote and put you in like that, there we go. We have basically our static states, as it were. Each of those static fields is one instance of the state that the game uses. To make the heroine jump, the standing state would also do something like, so if input equals press B, the standing state, the standing state. Okay, so we have the ducking state right here. So if we have the standing state, so for example, we copy you, we have a standing state that extends heroine state. We don't have a charge time. That's, hey, no. I already told you, no. Come on. Go away. So that goes away like that. Okay, handle input. Heroine input. Input is released down. Okay, so if the input is press B, then our heroine state is, so this is where we set to jumping. So heroine dot state, we now set this to heroine state dot jumping, like that. And then update, and then set graphics image jump. And of course, an update. So we're not going to have charge time anymore. So we don't have any of this really. This would really be just, we're going to move ourselves up. So it'll be this dot velocity y. What do we have for this? I guess we don't have like a velocity y. So velocity y equals like jump velocity or something like that. Instantiated states. Sometimes, though, this doesn't fly. A static state won't work for the ducking state. It has a charge time field, and that's specific to the heroine that happens to be ducking. This may coincidentally work in our game if there's only one heroine. But if we try to add two-player co-op and have two heroines on the screen at the same time, we'll have problems. In that case, we have to create a state object when we transition to it. This lets each FSM have its own instance of the state. Of course, if we're allocating a new state, that means we need to free the current one. We have to be careful here, since the code that's triggering this change is in a method in the current state. We don't want to delete this out from under ourselves. Instead, we'll allow handle input in heroine state to optionally return a new state. When it does, heroine will delete the old one and swap in the new one, like so. Okay, so we have our heroine handle input. So here's our heroine, its handle input. Our heroine state, is that a pointer? State equals okay, so state equals state handle input, this input. If state is not null, delete state, and then reset the state to whatever it was. So it optionally returns a new state. When it does heroine, we'll delete the old one and swap in a new one, like so. That way we don't delete the previous state until we return from its method. Now the standing state can transition to ducking by creating a new instance. Oh, okay. Because now so in heroine state, this is all, a heroine can potentially handle a new state. That's interesting. So heroine handle input, heroine state. Because let's see. So here's handle input. Heroine state. So this is gonna be this dot state. Equals. Oh, you know what? It's just a new state. So it's const state. So we would do const state equals this dot state dot handle input and add in the input. If state is not equal to null, then we want to delete the internal state and reset it to something else. Well, I mean, I could do delete state, but we could also just like overwrite it. And I think that in JavaScript, that would be fine for us to do this dot state equals state. So we're overwriting it. So if state is not null, set it to be this. So we're continuing on. So this still needs to happen. Right, because now in the heroine state, wait, that was supposed to be in the heroine. That was supposed to be down here in handle input. Like that. Now up here in heroine, in handle input for heroine state, if input is pressed down, okay, so here is if input equals press down, we want to return a new ducking state. Otherwise, if we reach the end here, we're going to return null. I don't know if I like this one. I don't like null being passed around like this, because then we have to check for null. Null is dangerous. I like setting things initially to it and then resetting to it, but I don't know. I don't like returning it explicitly. Let's see. So if input return new ducking state. So basically, we could do some other checks here too. I suppose, like what state they were in. When I can, I prefer to use static states since they don't burn memory and CPU cycles, allocating objects each state change. For states that are more stateful, though, this is the way to go. When you dynamically allocate states, you may have to worry about fragmentation. The object pull pattern can help. Well, I mean, I guess, sorry, but I'm still going to say heroin. Enter and exit actions. The goal of the state pattern is to encapsulate all of the behavior and data for one state in a single class. We're partway there, but we still have some loose ends. When the heroine changes state, we also switch her sprite. Right now, the code is owned by the state she's switching from. When she goes from ducking to standing, the ducking state sets her image. Okay, so heroine state, ducking state, handle input. So that's this one up here. If the input is released down, we're going to set the graphics to image stand, and we're going to return the new standing state. What we really want is each state to control its own graphics. We can handle that by giving the state an entry action. Right, because let's see, in handle input, return new ducking state. The ducking state does set its own graphics here. Okay, so class standing state. So here's our standing state. Then we're going to have an enter method. So when we start it, we begin switching over the graphics. So this would be an enter method where we get the heroine. And then here's where we have our set graphics happen at this point. Back in heroine, we modify the code for handling state changes to call on the new state. So I wonder if in the constructor we have to call enter. Or is this a C++ thing where it automatically calls this when a class is constructed? Because I don't see them like calling enter here. Okay, so in the heroine, it's a good point. I actually don't know. I don't remember the proper way of pronouncing it. I don't have like too many different jumbled ideas in my head. Okay, so back in the heroine, we modify the code for handling state changes to call on the new state. So we have, oh no, okay, so here's where we call it. In handle input, if the state is not null, we delete the state, set the state to the new state, and then immediately here, call on this dot state dot enter and pass in this. This lets us simplify the ducking code too. Okay, so our ducking state. If the input, okay, so this is the handle input. If input is released down, return new standing state. So we don't have to do the graphic stuff at this point in time. Right, because we don't want the image stand to happen in ducking state, because that's a little bit confusing. So we're instead going to say return new standing state. And now the standing state handles the graphics for that. All it does is switch to standing, and the standing state takes care of the graphics. Now our states really are encapsulated. One particularly nice thing about entry actions is that they run when you enter the state regardless of which state you're coming from. Most real-world state graphs have multiple transitions into the same state. For example, a heroine will end up standing after she lands a jump or dive. That means we would end up duplicating some code everywhere that transition occurs. Entry actions gives us a place to consolidate that. We can, of course, also extend this to support an exit action. This is just a method we call on the state we're leaving right before we switch to the new state. What's the catch? I spent all this time selling you on FSMs, and now I'm going to pull the rug out from under you. Everything I've said so far is true, and FSMs are a good fit for some problems. But their greatest virtue is also their greatest flaw. State machines help you untangle hairy code by enforcing a very constrained structure on it. All you've got is a fixed set of states, a single current state, and some hard-coded transitions. A finite state machine isn't even Turing complete. Automata Theory describes computation using a series of abstract models, each more complex than the previous. A Turing machine is one of the most expressive models. Turing complete means a system, usually a programming language, is powerful enough to implement a Turing machine in it, which means all Turing complete languages are, in some ways, equally expressive. FSMs are not flexible enough to be in that club. If you try using a state machine for something more complex like game AI, you will slam face first into the limitations of that model. Thankfully, our forebears have found ways to dodge some of those barriers. I'll close this chapter out by walking you through a couple of them. Concurrent state machines. We've decided to give our heroine the ability to carry a gun. When she's packing heat, she can still do everything she could before. Run, jump, duck, etc. But she also needs to be able to fire her weapon while doing it. If we want to stick to the confines of an FSM, we have to double the number of states we have. For each existing state, we need another one for doing the same thing while she's armed. Standing, standing with gun, jumping, jumping with gun, you get the idea. Add a couple more weapons, and the number of states explodes combinatorially. Not only is it a huge number of states, it's a huge amount of redundancy. The unarmed and armed states are almost identical, except for a little tiny bit of code to handle firing. The problem is that we've jammed two pieces of state, what she's doing and what she's carrying, into a single machine. To model all possible combinations, we would need a state for each pair. The fix is obvious. We have two separate state machines. If we want to cram n states for what she's doing and m states for what she's carrying into a single machine, we need n times m states. With two machines, it's just n plus m. We keep our original state machine for what she's doing and leave it alone. Then we define a separate state machine for what she's carrying. Heroine will have two state references for each, one for each, like class heroine. We have the other code, private. So we have the heroine state, we have the state, and the equipment. For illustrative purposes, we're using a full state pattern for her equipment. In practice, since it only has two states, a Boolean flag would work too. Okay, so basically, this is on heroine here. So essentially in the constructor, we could have equipment. So we could have a constructor. And I guess this is where we'd say this dot state equals null. Or maybe like we have an initial state, like the initial state is the standing state. So it would be new standing state. And then this dot equipment equals essentially, this is potentially a Boolean, so it could be just false. When the heroine delegates inputs to the states, she hands it to both of them. Okay, so in handle input on here, input. Okay, so this is where state handle input, this equipment handle input. That almost makes this go away. And now it's back to this dot state dot handle input, this dot equipment dot handle input. So I guess this would be something like new gun. Not that. Come on, VS Code. I'm not trying to do that. All right. A more full-featured system would probably have a way for one state machine to consume an input so that the other doesn't receive it. That would prevent both machines from erroneously trying to respond to the same input. Well, Rust makes that easy because we're just like, well, it's gone now, it's owned. Each state machine can then respond to inputs, spawn behavior, and change its state independently of the other machine. When the two sets of states are mostly unrelated, this works well. In practice, you'll find a few cases where the states do interact. For example, maybe she can't fire while jumping, or maybe she can't do a dive attack if she's armed. To handle that in the code for one state, you'll probably just do some crude if tests on the other machine's state to coordinate them. It's not the most elegant solution, but it gets the job done. Hierarchical state machines. After fleshing out our heroine's behavior some more, she'll likely have a bunch of similar states. For example, she may have standing, walking, running, and sliding states. In any of those, pressing B jumps and pressing down ducks. With a simple state machine implementation, we have to duplicate that code in each of those states. It would be better if we could implement that once and reuse it across all of the states. If this was just object-oriented code instead of a state machine, one way to share code across those states would be to use inheritance. We could define a class for an on-ground state that handles jumping and ducking. Standing, walking, running, and sliding would then inherit from that and add their own additional behavior. This has both good and bad implications. Inheritance is a powerful means of code reuse, but also is a very strong coupling between two chunks of code. It's a big hammer, so swing it carefully. It turns out this is a common structure called a hierarchical state machine. A state can have a superstate, making itself a substate. When an event comes in, if the substate doesn't handle it, it rolls up the chain of superstates. In other words, it works just like overriding inherited methods. In fact, if we're using the state pattern to implement our FSM, we can use class inheritance to implement the hierarchy. Define a base class for the superstate. Okay, so we have on-ground state. Great, because there's different things that can happen when we're on the ground. So, for example, here is this standing state is something that happened off the ground, and this ducking state is the other thing. So the superstate would be this. So class on-ground state, which extends this heroine state. Then we're going to have our handle input, which takes in the heroine and the input. Okay, so if input is press B, this is where we jump. Else if the input is press down, we're going to duck. And then each substate inherits it. So now we have ducking state, which inherits on ground state. Good morning, Chantilly. So ducking state now inherits from the on ground state instead of the heroine state. But of course, on ground state inherits the heroine state. How are you doing, Chantilly? Do you have a good weekend? Okay, so we do that. Public, virtual. Okay, so handle input. We have the heroine and the input. If we release down, we stand up. So that's where this standing state comes in like that. Otherwise, we didn't handle the input, so walk up the hierarchy. So interesting. So when we're in the ducking state, if we release down, we're in the standing state. But now, okay, so didn't handle the input, so walk up the hierarchy. On the ground state, handle input and pass in. What's interesting here is that this is a static method. Because I've overridden it here. So I suppose this would need to be static like this. Was it static before up here? I didn't see that. So now I can do on ground state dot handle input and pass in the heroine and the input. Yeah, just chilling most of the time. It's good to relax sometimes. This isn't the only way to implement the hierarchy, of course. If you aren't using the Gang of Four state pattern, this won't work. Instead, you can model the current state's chain of superstates explicitly using a stack of states instead of a single state in the main class. The current state is the one on the top of the stack. Under that is its immediate superstate, and then that state's superstate, and so on. When you dish out some state-specific behavior, you start at the top of the stack and walk down until one of the states handles it. If none do, you ignore it. Pushdown Automata. There's another common extension to finite state machines that also uses a stack of states. Confusingly, the stack represents something entirely different and is used to solve a different problem. The problem is that finite state machines have no concept of history. You know what state you're in, but have no memory of what state you were in. There's no easy way to go back to a previous state. Here's an example. Earlier, we let our fearless heroine arm herself to the teeth. When she fires her gun, we need a new state that plays the firing animation and spawns the bullet and any visual effects. So we slap together a firing state and make all the states that she can fire from transition into that when the fire button is pressed. Since this behavior is duplicated across several states, it may also be a good place to use a hierarchical state machine to reuse that code. The tricky part is what state she transitions to after firing. She can pop off around while standing, running, jumping, and ducking. When the firing sequence is complete, she should transition back to what she was doing before. If we're sticking with vanilla FSM, we've already forgotten what state she was in. To keep track of it, we'd have to define a slew of nearly identical states, firing while standing, firing while running, firing while jumping, and so on, just so that each one can have a hard-coded transition that goes back to the right state when it's done. What we'd really like is a way to store the state she was in before firing and then recall it later. Again, Automata Theory is here to help. The relevant data structure is called a Pushdown Automation. Where a finite state machine has a single pointer to a state, a pushdown automaton has a stack of them. In an FSM, transitioning to a new state replaces the previous one. A pushdown automaton, I keep on seeing automation, it's automaton, lets you do that. but it also gives you two additional operations. You can push a new state onto the stack. The current state is always the one on top of the stack, so this transitions to the new state, but it leaves the previous state directly under it on the stack instead of discarding it. You can pop the topmost state off the stack. That state is discarded, and the state under it becomes the new current state. Okay, so we have standing, firing, standing, and standing. So we push. Okay, so we're standing. Then we hit the fire button, so we push firing on top of firing. So we're both firing and standing. And then we pop that off when it's done, and we're back to just standing again. This is just what we need for firing. We create a single firing state. When the fire button is pressed, while in any other state, we push the firing state onto the stack. When the firing animation is done, we pop that state off, and a pushdown automaton automatically transition us right back to the state we were in before. So how useful are they? Even with those common extensions to state machines, they are still pretty limited. The trend these days in game AI is more towards exciting things like behavior trees and planning systems. If complex AI is what you're interested in, all this chapter has done is whet your appetite. You'll want to read other books to satisfy it. This doesn't mean finite state machines, pushdown automata, and other simple systems aren't useful. They're a good modeling tool for certain kinds of problems. Finite state machines are useful when you have an entity whose behavior changes based on some internal state. That state can be rigidly divided into one of a relatively small number of distinct options. The entity responds to a series of inputs or events over time. In games, they're most known for being used in AI. They're also common in implementation of user input handling, navigating menu screens, parsing text, network protocols, and other asynchronous behavior. Interesting. Okay. So if I wanted to implement a finite, or I guess like any kind of state machine into the infinite runners, what would it be? Well, we know that we have like the states of jumping and running. Or I guess like we have standing and jumping. Those are the two states that we have right now. And how are they implemented? So if we go into the P5, I think, does the player handle it? I don't know if we have. Okay, so we have this is jumping. Where is jumping? We have render, jump, apply force, hit ground, update. Wait, am I just not seeing it? Oh, okay, I see. So we have this is jumping. Is jumping isn't initialized. It's set right here. So when we hit the ground, is jumping becomes false. Okay. I have to keep on. I'm gonna have to figure out how to set it scheduled to not be during the stream. Okay, so jump, render. So when we jump, we set our is jumping to be true. And when we hit the ground, we set is jumping to be false. And so that's our state machine, I guess, as we're right now. But if I wanted to create like a class is jumping or maybe a function that's is jumping, then I could have handle our input. Come back to here. So we have our heroine state that's is jumping. I don't know if I need to do this pattern. It could be just the simple one where you have, okay, if we handle the state, if we can jump, where would we set, like where would we do that check to make sure that we can jump? So in our heroine, because we have 60 frames per second, and it takes more than, I mean, it might take about 1 second or so to like jump up and down, but that's many frames that's going to run. So all this code is going to execute many times. When we press the jump button, it's handling that over several frames because you generally hold it down for, I get like at least like I don't know, 30, 40, even 100 milliseconds. That's already several frames. So it would show that our input is jumping. So our handle input here for the heroine would get the input. Now, the heroine state is extended by all these things. I'm guessing, okay, so the heroine immediately gets a new standing state. The standing state gets its input. Oh, okay, so that's how it handles that. If we're in the standing state, we can transition to jumping. So we return a new jumping state. So heroine state jumping. Basically, we'd have a jumping state class too. Now, I wonder, based on what he was saying before, if we have a function for the standing state, I mean, because we could just have, instead of making this a class, we could just make this an object, sort of like const jumping state equals an object that's going to be handle input, which brings in heroine and input, and it's also going to have what is that? Update. So if we do something like this, then we don't need it to be the class. It's just existing here. We can create new ones of these by just, well, assigning the jumping state. I guess creating a new jumping state. Well, how many, like, do we really need a new jumping state? We just say, okay, if we're in the jumping state, when we land on the ground, I guess that would be like if we land on the ground, then we're going to handle a new, so that would be under update, wouldn't it? So maybe we can check like if heroine is on ground. Okay, so if we're in the jumping state now we want to return the standing state. Something like that. And of course, if we have just objects like this, it would just be return the standing state. Otherwise, and so what this might look like is if heroine, I don't know if I want to do like the calculation here, or if it will just be something like dot is on ground. It'd be something like this. So if we're not on the ground, then we want to that's interesting, because if we're on the ground, I guess because the jumping state can handle its own internal state. Oh, so that's where we have the entry, right? And that might be where the class is easier, because then we can have a constructor with it. So when we create a new one, it instantiates it and like sets it up. So instead of an entry like here, we put that into the constructor, and then we don't have to remember to call the entry, which then we might call the entry too many times. Because here, if I do have an entry, how do we know when to call that? I guess we call that here, return a new, like set a new standing state, call the entry for that. So the class might be a little bit easier for us just because of that. But like if I make this, do we have a jumping state? We have, we don't. Okay, so if we have class jumping state, we'd have a constructor. This dot like, have we started jumping? Like, I guess, are we on the ground? If we're on the ground, we want to give that initial sort of momentum up. Otherwise, it's just gonna apply the gravity as normal. Okay, so we would begin jumping. So this is where we'd say if, and we probably need to pass in the harrowing to know exactly what's going on. So actually, I guess if we were in the jump, we know that we're starting, don't we? So we need to set the initial, so apply initial up velocity to heroin. And then that's it. That's sort of like our entry for that. Then in handle input, here's where I guess like there's not really much to handle for input for this one, because if we're in the jumping state and there's no input to handle because we're just going. Maybe we're allowed to like move left and right. I don't know. And then in our update, if we discover we're now on the ground, now we're going to return a new standing state. So we leave the jumping state right then. Otherwise, so maybe we have like an else here. And now we're going to just apply gravity. So we could have heroin dot apply, be something like apply force and pass it in the gravity force. Something like that. All right, well, that gives us something to look forward to starting